Welcome everyone. My name is Sasha Rubin. I'm the academic coordinator of this seminar series along with Julia Ashworth. A little bit of logistics before we get going. So this is, as you know, the school seminar series called the Vassar Seminar. It's named for Adolf Vassar, who was in the 1950s, helped fund, basically paid for the university's first computer. We hold a seminar once a month. Next month, one of Rahul's visitors will be speaking. In June, we have no seminar scheduled. So the first open slot is July. So if you know anyone, if you have any visitors, be they from academia or from industry, please get in touch with me. For today's talk, as you can see, the talk is being recorded. So will the Q&A at the end. The speakers asked for questions to be held till the end of the talk. And with that, I'd like to actually introduce Professor Judy Kay, who will introduce our speaker. Judy.
Thank you. I'm delighted to be able to introduce you. I'm really sorry I wasn't able to be on campus today. Hideki and I have both been doing research for some time and share some of the same research communities, in particular the often renamed, but now interactive surfaces and spaces, looking at the ways that we can really create and harness new technology for all sorts of things that people would like. And I'm particularly excited that this talk is about an area that I'm passionate about, which is helping people learn, using technology to augment our ability to learn. And he has a distinguished track record of amazing papers across all sorts of places, SIGGRAPH. I've mentioned interactive surfaces and spaces, Chi, WIST, and I particularly remember his beautiful, memorable spherical interfaces that were really exciting and interesting to learn about. But I think that it's exciting that this particular talk continues a long thread of finding ways to create technology for one of the most fundamental of human skills, which is what probably makes us human, our wish to learn, and crossing areas as diverse as skiing and speaking and, well, quite extraordinary, learning the piano. So I'm really looking forward to the talk, and I hope we can all welcome Hideki.
Thank you very much, Judy. And thank you, Anusha, and everyone who invited me to this great presentation. So today I want to talk about my recent research, skill acquisition and transfer systems with AI and XR. And before I'm going to the presentations, I just briefly mentioned about our university. I'm coming from Tokyo Institute of Technology, and which was established in 1881, not so old as University of Sydney, but we are national universities. And it is very sad that we will merge with Tokyo Medical and Dental University and changing our names to Institute of Science Tokyo. I'm not sure this is a proper English or not, but they insisted on using the Institute and Tokyo. So we do not have a choice because there are plenty of universities in Tokyo. So maybe 100 or so. So we don't have any choices. But anyway, so our university is out of the Tokyo, and it's just 20 minutes from Shinjuku Station or Tokyo stations. So if you're planning to come to Tokyo to attend the Chi conference next year, which will be held in Yokohama, so it is very close to our campus. So I will organize our lab tours during the Chi conferences. Please come to Yokohama and Tokyo. So I'm going to skip these slides because I showed it in the Augmented Humans Conference, but we have two Nobel Prize our professors, and please ask me about the Baymax after my presentations. Anyway, so I'm going to talk about those kind of topics today. And before I'm going to the skill acquisition researches, I'm going to recap my past researches. First one is interactive surface technologies, which Judy mentioned right now. And first one is I did work on transparent 2D markers on LCD displays. So as you know, the 2D markers is always used on the interactive surfaces, but the 2D marker is black and white patterns, which is not no meaning for humans. So I want to diminish, I want to, I do not want to see such black and white patterns on augmented reality research. So we designed those transparent markers, which just works on LCD displays. Yes, videos. So this is transparent markers. It looks like transparent, but if you put the polarization filters on cameras, you can see these black and white patterns. And by using this, we can use these markers as a normal AR markers or QR codes or something like that. But one of the designing advantages in designing is since the users will not see the marker patterns, we can design very natural and intuitive interactive systems on the LCD displays. Okay, so the next one is aquatop display. This is the interactive surface on the water. So since we have a culture, we Japanese have a culture of bathing. So we spend a lot of time, a lot of hours sometimes in the bathroom. So we want to make this the water surfaces are interactive surfaces. So we did it by using projectors and the Kinect cameras. So here's videos. So he can scoop the information on the surfaces. And we presented this work in SIGGRAPH and Laboratory and anywhere in the world. And we received a lot of awards in this. So this is not a touch panel, but the Kinect camera on top of the water can detect the user's gestures, such as pinching or poking or pinching by using two fingers, just like that. Okay. The third one, that's final one, is ball cam systems. Since I'm a very good, sports lover, so I want to see the ball sports from inside the field. So I want to put the small cameras in the balls and to broadcast that sports inside the sports field. But the problem is the ball is spinning so fast. So that is a problem. So here is our solutions. So this is a sample scenes when we put the small cameras inside the bowling ball. So it looks like this. So it doesn't mean nothing to the humans, but we cancel the rotations of the cameras by using computer vision technologies. So this is a sequence. So if we pass the balls with camera, it looks like this. But if we use our stabilization algorithms, it can be looks like this. So even if the ball is spinning so fast. So next one is my favorite videos. This is taken from water polo. So original video looks like this. But if we adapt our stabilization algorithms, it looks like this. Okay. So let's go on to today's topics. So this slide shows the background of my current research is the skill transfer. So the first, the athlete's music performance or handicapped person, such specialist has a very special skills which we ordinary people do not have. So we want to capture or we want to acquire such skills from the experts and make some databases and transfer that skills to ordinary or expert as well. But the problem is currently such kind of skills are captured by using motion capture systems. But motion capture systems is very expensive, as you know. And most importantly, such motion capture systems can be used inside the rooms, usually. So we do not have a real-time feedback to learners right now. So we have to show the videos like this after the training, or we want to stop the movement of the athletes like this. So our main purpose is to capture the user's motion as easy as possible and as low cost as possible. And also, we want to give the real-time feedback to the athletes or pianists or vice versa. So this is a concept of our project. So this is a very famous figures in brain sciences. So here is the humans, and they have some desired states like this. This is a desired state of experts or something like that. And he has some estimated state like this. So if there is a differences between this state and this state, he will give some motor feedback to their muscles to fix their positions to the desired states. But the problem is, this is the expert positions, but this is the imaginary positions he is thinking. So there is some differences between this desired state and his imaginary state. So we want to show those differences by using visual, audio, and haptic feedbacks using, let's say, the XR technologies. And before that, we have to sense those postures as easy as possible. So we need a sensing technologies. So that's why I'm going to talk about the sensing technologies first. So before that, this is a democratization of skill acquisitions I'm currently thinking. So this is the current situations of motion capturing. So we need lots of cameras, and the experts can be only users, not the normal persons. And since because of this, we have a very small data set. But after the democratization of our skill acquisition systems, we can easily acquire the pose or skills of these ordinary persons in very low cost. So if the motion capture system becomes very low cost, then many people will use these systems, and then the database becomes larger and larger, bigger and bigger. So it becomes the deep learning technologies much smarter and smarter. So we could give much more scientific coaching to the users. So the first technologies I want to talk is a 3D head body pose estimation using chest-on cameras. So as I talked to before, to capture the motion of the users, we need 8 or 16 cameras inside the room. And also, if you want to capture the gaze direction of the users, you need another equipment such as wearable glasses or some fixed cameras or so. So it costs a lot. So we design, we design very small cameras which attached on our chest. We just use one cameras on the chest to capture the motions and also capture the direction of the head, not the gaze, direction of the head. So here is images from the cameras. Unlike the normal action cameras, we attach a very ultra-wide fisheye lens on this action cameras, which has 28 field of views. So it can capture his face and hands and legs as well. So as if you see these images much more in detail, you might see the hands and foot and his face around here. So we use the three convolutional neural networks to estimate his 3D pose and 3D head, and also camera orientations. It is important to correctly know his 3D human poses. Let me show you the videos.
We present Mono Eye, a multimodal human motion capture system using a single wearable device. The user simply wears a portable chest-mounted camera to use the system, and also it doesn't require any markers or calibration procedures. The ultra-wide fisheye lens of our hardware setup has a 280-degree field of view and can capture the user's limbs, lower face, and the surrounding environment. We realize a multimodal motion capture which includes 3D body pose, head pose, and camera pose using multiple lightweight deep neural networks that consist of camera pose net, body pose net, and head pose net. Combining the outputs of the deep neural networks, our system can capture the camera pose-aware 3D human pose and the viewport of the user without any additional sensors.
So this is a viewport.
To train the deep neural networks, we have generated a large-scale synthetic dataset. 680K of images were rendered in a variety of body
to collect the number of data set. But there are lots of first person's view data set in the world, as you know. But there is no those fisheye lens, those kind of image data set use the ultra-wide fisheye lens. So we have to prepare this data set ourselves. So we use virtual humans and virtual cameras inside the Unity world to which has the same parameters as parameters of cameras we used.
Shapes, clothes, motions, and backgrounds.
So we change the
body
body of
net
the
estimates
users
the
and
2D
also
heat maps and the
background.
camera
or
relative
something
3D
like
position
that.
of the user's
So here
joints.
is
By
estimated
applying the
point
camera
of
orientation
joints.
obtained by camera pose net, the proposed system can recognize the poses with the same joint position and different camera orientations. With these methods, our system enables accurate motion capture with a portable wearable device.
As a collaboration between our university and Carnegie Mellon universities, we use Carnegie Mellon
Head pose net
University's
estimates the
Panoptic
user's head
Studios
pose from a
to
lower
get
face image captured by the
grand tools.
chest-mounted camera. We can crop the user's viewport from the ultra-wide fisheye image using the estimated head orientation
which was
and the net
generated
position.
from this input
The
images
estimated viewport
and
is
his
as accurate
head
as the
motions.
images taken with the head mount
So this
camera.
is the actual viewport,
So the user
which
no
was
longer needs
taken
to
by
equip
a
their heads with
camera which is
inconvenient
attached on
equipment
head.
for the first-person view capture. This rich information can be utilized in many end-user applications.
As an application example, it
With
can
our
be
lightweight
used for
hardware
motion capture
configuration,
systems
we can
or
capture the user's
making
motion accurately
to
anytime,
generate
anywhere.
the
The
avatar's
user
motion or
just wears
something
the
like that.
camera on the clothes that
Okay, let me skip on this. And this is an evaluation of our technologies. The MPJP, the mean per joint per mean position of joint to mean mean position of joint per sorry, I forgot. But anyway, I'm so nervous right now. So MPJP is in 43 millimeters in average, But in case of the upper bodies, it is just like to 24 millimeters in average for each joint, for joints. So it looks like not so good as traditional motion capture systems. But if we collect a much more larger number of data set, especially the real world data set, not the synthetic data set, it could be lower and lower, I think. So since this camera is not only captured our motions and also our surrounding environment, we could apply the normal human pose estimation technology such as OpenGL to estimate the pose of the users in front of the wearers, like this. So this is our this slide shows the social acceptance of our technologies. There are so many first-person view projects which has the cameras on head or eyeglasses, but we think our chest-worn camera is much more socially acceptable because it becomes much more smaller. Than it could be a pendant, or it could be a tie-pin, or it could be a button of the shirts. So if we talk about this, some people in Japan always asked me that, but your camera is so big, and it's going to be a 10 or 20 years later, but it is not, because we already have those kind of very small cameras. So if this camera has a 28 or 25, 280 or 250 degrees of viewport, so we could do the same things by using these small cameras. So our dataset is open in our GitHub databases. So if you are interested, you can use our dataset freely. So next topic is 3D hand finger pose estimation using a wrist-worn camera. So one of our motivation is to use these technologies to estimate our gestures, recognize our gestures, hand finger gestures. But since as you are familiar with these technologies, so if you want to recognize the hand finger gestures, you have to make your gestures in front of the cameras. So if this PC has the cameras, we have to go in front of this PC to make our gestures. So this makes those kind of gesture interface much not popular. So our idea is to use the cameras which is attached on the crown of the smartphones in here. Because the smartphone is getting popular and popular, it will be much more socially acceptable in the future. And if we have a camera in here, we could use the gesture technologies without go in front of the big cameras or something like that. But the problem is, can we estimate or recognize the gestures just by using a camera in the crown positions? But we can. So let me show you the videos. So this system is called backhand pose.
Interact with objects with their hands because it is the most natural and direct way which poses many degrees of freedom. Therefore, a huge number of wearable hand tracking devices were developed.
As I said, that you have to do your gestures in front of the cameras.
Let me skip. A camera placed on the
so this is
of the wrist.
Result of
this camera is
hand finger
considered to be easily
estimations.
Into
So here is
devices, such
cameras,
as
which is designed to
our system employs deep neural network to extract
designed
indirect
to
temporal
be the
features
position
on the back
of the
hand,
crowns
such as the
of the
deformation of the
smartphones,
muscles,
smartwatches. Sorry.
tendons, or bones.
So this is
through
images
joint angle-based
taken from
impulse.
the
before
cameras.
inputting to the networks.
So as you
The
can see,
obtained
you can
player
just
also
see
have
the
masks.
backhand
The images are
of the
preprocessed by an
hand,
autoencoder
but
for background movement.
thanks to the deep learning technologies, we can estimate the hand finger poses very
At the
precisely.
same time, the motion history images,
Not only
which
the
is the other stream
RGB
passed
images,
to the network,
we use the
are
image
calculated by
history
observing the
of
wisdom
the,
of the 5-part
the
masked images.
textures
Our
of the
network is
backhand.
based on a two-string residual
So
convolutional network, which
this
was
is
further processed
the
by an
overview
LSTM-based
of our
common filter
deep
for
learning
temporal feature
networks.
extraction.
But anyway, so this is the
Here, we
real-time
are showing
results.
some
Here,
real-time results in different conditions.
here is the estimated finger hand poses. So as you know, the lighting condition is very important in computer vision researches, but our technologies can also be used in very dark conditions, also very bright conditions. Okay, so, but this is a variation of our results. So as for finger angle estimations, we found that our system will estimate. This is a joint the error of angles. So our system is that has a 10 degrees or less than 10 degrees, 10 degrees of errors. It looks like a little big, but those are the state-of-the-art technologies for the finger recognitions by using cameras. So we succeeded to make it much more smaller. So when I talked about these technologies to the person in Japan, they always asked me that, oh, it's going to take 10 or 20 years to get such smart watches, but it is not. We already have smart watches which has a camera on the crown. So, and if they want to use our technologies, our softwares could be used in this watches to capture our motions. Okay. The next one is the real-time 3D human pose forecasting with RGB video cameras, which was presented in augmented human conferences. So
the demonstration was conducted using
we
normal RGB
tried
webcam,
to
while posts of 15 frames before are forecasted in a
forecast
30 fps video.
the user's poses by using deep neural networks. So this red skeleton shows the estimations by systems. So even if this man do not jump, before his jumps, this red skeleton is forecasting his body poses by using our deep learning
the demonstration was
systems.
conducted using normal
And
RGB
this can be
webcam,
also
while posts of 15
applied
frames
to
before are forecasted
forecasting
in a 30 fps
the
video.
ball, not the trajectory, that the touching point of the ping pong balls in here. This green circle shows the ground truth, and this red dot shows the estimation of the systems.
The demonstration was conducted using normal
Okay. Oh, here is a much more bigger.
Human beings are always
poses.
doing prediction on human motion from their present vision, hearing, or tactical sense. Among them, vision-based motion prediction might be one of the most commonly used behavior. Therefore, we propose future pose, a pose estimation system based on deep neural network. With no more RGB frames as input, we can obtain the future pose position of 2D and 3D. And our contributions are fourfold as follows. Our network consists
After
of
developing
customized
these
residual
technologies,
network for
we
pose estimation, and it also learns
talked
temporal
about
features through
the
their
application
optical
of
flow and their
this
sim layer.
technologies to
We also
the
propose a sparse optical
the
flow method. By
sports
calculating the
expert,
optical flow of lattice points and
particularly
averaging them with the estimated joint
the
position,
volleyball
we can obtain the joint
players
movement instead
and
of
also
using dense optical
table
flow, which
tennis
leads to a
players.
faster computation
And they
speed.
said that
The
it
forecasted
may be
utility process
useful
recovery
because
through 3D is through simple
in
linear regression.
case of top athletes, it is
The
very
demonstration was
important
conducted using
not
normal
to
RGB
be
webcam, while posts of 15 frames before are
estimated
forecasted in a 30 fps
their
video.
next poses by opponent. So they could use this system to minimize their some how can I say the features when they turn left or when they turn right. So by minimizing those small movement, it is
The
very
outputted 2D
difficult
pose position
to
are filtered to reduce the
estimate
noise.
the next poses. Okay. So the next topic is there are plenty of topics. So next topic is the haptic feedback systems. So as you know, there are some exoskeleton gloves like this. So they intended to give a haptic feedback to the hand. When they are using virtual reality technologies, they want to give some feedback when they grab something in virtual. But the problem is those exoskeleton gloves are very big and very heavy and very, how can I say, not comfortable to wear. And also, those haptic gloves can, for example, pull your fingers, but not push, just one directions. So we designed another technologies by using this pneumatic artificial muscles. Are you familiar with the pneumatic muscles? This white line is a pneumatic artificial muscles. If you put airs inside, it will shrink 25%. So it's gonna be a kind of actuators. So we put totally the 20 artificial muscles on one hand by referencing the human's anatomical architecture. So here is videos. So it can push your fingers and pull your fingers. This is a demo videos. We do not want to we not want to give such a force. So our aim is to teach the poses or timings to each fingers. He couldn't play the Fiore Elise 10 minutes before the experiment, but after he learned the position of the keys, the system will teach him. System taught him when he hit the keys. So we apply this soft exoskeleton gloves to the expert pianist, and we invited 5 expert pianists, including a professional pianist, to our experiment, and we asked them to play the piano as fast as possible. After that, we make them wear our gloves and make their fingers move as fast as possible, faster than their limitations. And after they take off their gloves, it is interesting, their fingers moves faster than before. And the most important thing is we make them wear the gloves on their right hand. We did experiment with the right hand. But after the experiment, their left hand also moves faster. So this is very interesting insight from our researches. I'm not sure about this results, but this was done with Dr. Furuya of Sony Computer Science Laboratories. He's a very expert of science of pianos, and also brain sciences. And he expected that there is some something happens in the brains, and if your right hand moves faster, it's going to happen in your left brain, and it will affect to the your right brain, and it makes your left hand faster. So we also want to use this gloves for rehabilitation purposes, particularly for a person who has after effects of stroke. So we make them wear our gloves on their impairment, the hand which do not move, and which has to move, hard to move, and we make them wear the gloves, data gloves on their right hand like this. And this is inspired by mirror therapy. This is very popular application technologies in after effects of strokes. So he's a voluntary patient who came to our laboratory, and his left hand didn't move so well. And when he grabbed his right hand, and our glove tried to make the same poses as the right hand. So he told me that this has a potential advantages, and but to make it much more practical, he told us that we need some the elbow and shoulder support, not to move the elbow and shoulders. So we are currently redesigning our gloves. Okay, let's go on to the some training systems, since we don't have enough time. So first one is alpine ski systems. So are you familiar with the alpine skis? Maybe yes. Okay. So, but the ski is very popular. But you have to go to the ski slopes. You have to have with snows and etc. So we are using this big ski simulators to capture the motion of expert skiers who is national team members or the World Cup racers or Olympians in Japanese. So we capture their motions as well as foot pressures and EMG signals, and make it a database, and comparing those between each athlete. And after that, we use these motions in a virtual world to for the novices or intermediates to how to ski inside the virtual simulators. This is the virtual ski simulators. This is a very small versions, and it doesn't cost so much. And, he's wearing HMV, and he's seeing virtual ski slopes. And in front of him, he's seeing expert racers, which was captured by this ski simulators. And he asked to mimic the expert's motion as well as follow the ski lines the expert made, because it is very efficient to run skis. Efficient to efficient to ski just after the expert skiers, but it is sometimes dangerous. So we make those kind of virtual skis. So if you have any questions, I'm happy to answer in the questions and answer sessions. So this is the top racers in Japan. So and also, I'm one of my current research is to make the ski learning systems for visually impaired persons. So this is an image from the Paralympic. So this is the guide, and this is a visually impaired person. So this is very crazy, and I want such visually impaired person to ski much more and more, but it is very difficult because it is dangerous, and also it is very difficult to have the volunteering persons in the ski resort, ski areas. So that's why we make those systems on the ski simulators like
the
this.
effectiveness of the feedback system. We
So
conducted an
those
experiment
four
with
people
4
are
V
the visually
skiers.
impaired
Evaluate the
persons.
effectiveness of the feedback system.
Instead,
We conducted an experiment with
although
4
we
V
have
skiers. Evaluate the effectiveness of the feedback system.
the screens
We
in front of
conducted
the
an
screens, they
experiment with
couldn't
4
see
V
anything.
skiers.
So
Evaluate
they
the
have just
effectiveness
a
of the
sound
feedback
feedback
system. We
from the
conducted an
systems
experiment with
when
4
they
V
have to
skiers.
start
Evaluate the effectiveness of the feedback system. We conducted an experiment with 4 V skiers. Evaluate the effectiveness of the
So
feedback
after
system. We
they
conducted an experiment
train
with 4 V
on this
skiers.
ski
Evaluate the
simulators by
effectiveness of
using
the
audio
feedback system.
feedbacks,
We conducted an
they could go
experiment
to
with
the
4
real
V
ski
skiers.
slopes
Evaluate the
to
effectiveness of the
do
feedback
the next
system. We
steps
conducted
of
an
their
experiment
skiing.
with
That's
4 V
our
skiers. Evaluate the
proposal.
effectiveness of the
And
feedback
also
system.
currently
We
we
conducted
are
an experiment with
attaching
4
our
V
chest worn
skiers.
camera
Evaluate the effectiveness
to
of the
them
feedback system.
to
We conducted
capture
an
the
experiment with
environment
4 V
and
skiers. Evaluate the effectiveness of the feedback
to
system. We
recognize
conducted an
the
experiment with
obstacles
4
or
V
humans
skiers.
or
Evaluate the
trees
effectiveness
in
of the
front of
feedback
them
system.
to
We
give the
conducted an
some kind
experiment
of
with
sound
4 V
feedbacks.
skiers.
But it could
Evaluate
be
the
a
effectiveness of the
long
feedback
range
system.
researches. Okay. So next one is the golf training systems. And the main idea of our technology is to capture his motion and the club trajectories by using motion capture systems, and then project everything on the floors. Because in case of golf, you have to focus on the ball to hit the ball. So you can't see anywhere when you swing. So we use their peripheral vision to see the visual feedbacks. And it works very fine. And also, we are capturing users' motion by using a real-time motion capture system. But also, we have expert motion data, which was previously recorded. So one of the academic challenges in our system is how to match the real-time users' motion and the pre-recorded experts' motions. In here, sorry. Okay. So here you can see the virtual shadow of himself. And also you will see white contours around him. This is the expert motions. So this expert motion was searched inside the expert database and projected onto the floor and simultaneously. And this is the projection of a club head. And the club trajectory is very important in the golf swings. Most of the amateur or novice users has outside-in trajectories, which causes right slice of the balls. But if you see these club trajectories, you could easily understand your swing is inside out or outside in or else. Okay. And we're also using AI technologies to find which part of his swing is not good. So let me talk about it very brief. So here is expert motions, and this is a novice motion. This is me. And one of the issue is the timing and speed of the swing is different in each players. So we have to first synchronize these two motions by using autoencoders. So after we put those multi-parameters inside the latent space, we put those positions in here and then synchronize the typical positions such as address and backswing and top positions. And after that, we could detect the positions where there is slightly large differences between this and this. So by using an autodecoder, we could reconstruct the which part is good for them. Which part is very different between expert and novices. Okay. So this is the different timing, and we first synchronize those two movements like this. Okay, let me skip. And the final one is on piano training. So we need our final goal is to make a piano training system for expert as well as novices. But to do that, we want to capture the hand finger motions very precisely without using our wrist-on cameras because it takes a little time from now. So one of the solution is to use motion capture systems like this. But in case of this, we need to put many markers on the hand. It takes a very long time, maybe 30 minutes or so, to prepare for the capturing. So we designed and developed systems which do not require such pre-processing, and we make many piano data set by using our systems. And as you might be familiar with the media pipe, which is a general purpose gesture and hand recognition libraries. But media pipe is designed and also used generic finger hand movement. It is not for piano playing. So it sometimes has a very big differences between the estimated position and the ground truth. So we use the piano data set and succeeded to correctly recognize estimates his 3D hand finger positions. Sorry, I don't have enough time. So this is applications which use head-mounted displays to show her motions and her teacher's hand motions simultaneously. Some people asked me if we need such systems for expert pianists, but the expert pianists told us that this is a very promising approach to learn their hand finger positions when they are playing. Okay. So we have lots of another skill acquisition work, but maybe I should stop around here. And if you have any questions, I'm happy to show another researches of our skill acquisition technology. Thank you very much.
I have a small question about sort of fishbowl camera and the social aspects of that.
Okay.
So I know personally I would be very uneasy with knowing that people can just hide a camera in their pendant and go around. But like, has there been any study about how people react to that, especially in terms of emotion and like how people interact, especially in the context of having facial recognition deployed in crowds during protests, etc., because that could be used for that.
Are you talking about the privacy issues?
Yeah,
And social acceptance issues. Okay, yeah, that is one of the issues of wearable cameras, like you see. And we are also thinking about that. In that case, we could use, let's say, some kind of masks for the cameras, not to capture the front motions, or we could use another kind of, let's say, the infrared cameras, which has a very short distance of focuses, not to capture the other persons. But anyway, it depends on the applications. Thank you.
Any questions on Zoom?
Sure, I can ask a question. My name is Tim Scott. I'm a rehab doctor at Sydney Children's Hospital. Anyway, that was a great presentation. What a tour of fantastic applications. I'm interested. I just wanted to ask about the glove, the pneumatic glove for the stroke people. And I was watching your video, and it showed this the movement. So I'm just wondering. I mean, I think with retraining and using those sort of networks, mirror therapy has been shown to be pretty effective, and I think it's a really good application. I just wonder, you're going to get some strong spasticity in many patients, and it's going to your glove isn't going to be able to handle much of that without breaking either themselves or itself or the patient. I'm just wondering, things like Botox can be used together with, this sort of technology to be really effective and provide movement while it's sort of reduced abnormal muscle tone. Are you exploring that at all?
Okay. First of all, this is a very first prototype of our researches, and we have not yet hired many volunteers. He is just one person who accepted our experiment. And as you said, that we need much more integration of these systems. And but personally, I think this is a very promising technologies. And since he has spent many years after his stroke, and his left arms becomes kind of solid. How can I say? But
Stiff, yeah.
Yeah. So if we could do those kind of rehabilitations in the early stage of his stroke, after strokes, it might be much more better. It might have much more better results since their hand is not so still. So, does it answer to your question?
Yeah, no, that's a good answer. I think early intervention is really effective, but also I think I wouldn't write off later intervention as well. And I think in conjunction with with surgeons and other techniques to release tight joints or muscles, there's a lot of potential in the collaboration.
Yes. Thank you very much.
Any further questions?
Mentioned how training one hand leads to better performance in the contralateral hand.
Are you talking about the piano training?
Just the piano training. Yeah. So maybe there's some kind of co-priming of ipsilateral and contralateral brain region. I wonder if you could potentially do an experiment where you put two gloves on, one's just randomly vibrating while the other one's being trained.
Well, we haven't yet done such kind of experiment, but Dr. Huri is very interested in such kind of technologies because he is working on the how to break the barriers of the expert pianists, as well as some patients who are suffering from, how can I say, the pianist who could not move the typical movement because of his nervous. He said this kind of haptic technologies might not only their muscles but also their the brains. So it might solve such kind of issues. So we will keep working on these systems.
What's the Mono Eye project? I noticed that with all the images that you showed, a lot of those kind of like light field capture from different environments. So one of the big problems with radiance mapping is that you generally have a fixed camera acquiring the light field for just one point in that environment. But here you have a situation where you can basically move with that. I was wondering whether you're exploring AI opportunities for sort of like very dynamic encoding of radiance maps for real-time rendering.
Are you talking about developing the data sets or in the
could be used potentially for creating real-time rendering opportunities. So when you showed the avatar, for example, the skiing that was kind of like in a very impoverished environment, because you had information about the light field, you potentially could render in real time, change the coordination as people move through an environment.
Yes. So as I told you, we make the virtual. We use the virtual humans in the virtual world to make such kind of data set, and we try to change the environment as possible as we can. For example, as you see here, we make a different textures of the users, and we make we use a different body shape of the users, and also we use the different background, the different lighting conditions inside the virtual world to make the data set as near as our real environment. So,
Judy, have a question.
Okay.
Hello.
Last question, Judy.
Thank you for the amazing tour of wonderful things you have done. I wondered, in the ones that you have built to help people learn, a lot of it provides immediate feedback, but I wonder, say, take the piano one, whether you have, one of the things I'm really interested in is capturing long-term learning data so people can see their progress over the long term, and so that they can, sometimes you're not aware of what you're doing right, what you're doing wrong. And maybe I can see a lot of your applications that's being tackled in a very subtle way. But I wonder if there is a place for a conscious interaction with the user so they understand better where their problems are if they aren't aware of them, and whether that, and the opposite as well. Does that make sense?
Okay, thank you very much for your questions. So yes, so it is very important to compare their long-term progress in piano as well as the sports. And since our technologies can capture and record each motion, so in case of the piano trainings, we can record and records the learner's movement, and she or he can compare his past data with his or her current finger hand motions. So it makes them understand the progress of themselves in a long-term learnings, I think.
Let's thank once again Professor Koike for a wonderful talk.